Previously, we've talked about objects that can speed up and slow down. And what we did was we learned how to predict the velocities of objects if you let them accelerate for a certain amount of time. And we came up with what I tend to like to call our first equation of motion. And that was an equation, I'll just write it down over here, that related final velocity to acceleration, some final clock reading, and then initial velocity. And using that equation, we're able to predict, like I said, a final velocity if we know something about our acceleration and our initial velocity, and of course, how much time has elapsed. But interestingly, what you don't see in this formula is anything to do with position, where an object is located, and that's critical. We need to get a formula or some way of thinking that will allow us to know exactly where an object will be along a number line here if it is allowed to speed up or slow down. And this formula is limited. It doesn't tell us that information. So that's what this video is about. And we're going to learn how to predict the position for objects that speed up and slow down. Now let's take a step back though and consider constant velocity motion. And take a look at this little car and make a prediction. Where's this car going to be located in 4 seconds? Pause the video and do this. It's really easy. All right, well, hopefully you reasoned that it's constant velocity, 1 meter per second. So after 4 seconds, it will have moved forwards by 4 meters. And that would put us right here at a location or position of positive 1 meter right here. Okay. Now, our constant velocity model equation allows us to just plug in numbers to figure that out as well. So let's do that. So we would plug in an initial position of negative 3 meters, and then a velocity value of positive 1 meter per second, and then I gave you the time of 4 seconds. Perfect. So very easy. You should be able to do this no problem. And we get the plus 1 meter for our final position. Cool. All right. So now, however, I want you to imagine that maybe when we're halfway to this spot, to 1 meter, okay, which would mean we're at negative 1 meter, maybe somewhere right here, and I'll just redraw the car quickly. Somebody decides to step on the gas, and now all of a sudden we're going faster. Now I'm not even going to tell you how much faster we're going. I'm just going to say faster. Faster than 1 meter per second, okay? We still allow this thing to travel for 4 seconds. Now make a prediction about where on the number line you think this car is going to be. You think it's going to be before plus 1 meter, still at plus 1 meter, or further over here after plus 1 meter? Make a prediction. Go ahead, pause the video. All right, so pretty easy question. If somebody stepped on the gas or the accelerator, say this is a car or something, and it's going a little bit faster, you're going to end up a little bit further over here to the right of 1 meter. So that kind of begs this question, well, how can we predict that? If we inspect our formula, and I'll just write it again, final position is equal to our constant velocity times our final clock reading plus initial position. If you look at this, we don't have any way in this value for velocity to plug in different numbers. It's just one variable. So we could plug in 1 meter per second and make a prediction like we did. And then if we went faster, well, what do? Plug in the new speed, right? Plug that in there. Well, if we did that, that wouldn't be taking into account this previous slower speed. So how do we work it all out and add it all up properly so we predict the right position? That's what we're going to learn here. And what's even nicer is that we don't even have to have like a big table of all of the speeds that it's going to be traveling at through the motion or anything like that. We can consolidate all that information about how fast this object goes at any moment in time with the concept of acceleration. And so we'll see that variable a, which we used for acceleration in a previous video, which again has units of meters per second for every 1 second. And we'll see how this singular number here in combination with an initial velocity, so kind of like a starting velocity when the clock reads 0, with these two ideas, we'll be able to build up a formula for final position. So let's see how to do it. All right, so in the perfect case, I should be able to now just say, hey, pause the video and then figure it out. I've given you enough information on the slide here for you to be able to derive this. This is what we're doing here. We're deriving something in physics. But I want to help you out a little bit. So go ahead and I'll remind you up here of the equation of the line that we're looking at right now. We've got a graph of velocity versus time, and we see a linear line going up like this. We've seen this before. And think to yourself, what is this object doing? Is it speeding up, slowing down? What direction is it moving in? Pause the video and make sure you see that first. All right, well, this particular object is moving in the positive direction because its velocities at any given time are all positive above this horizontal axis here. Okay, so it's moving in the positive direction, and then you can see that the magnitudes of the velocities are increasing. They're getting larger and larger. This, what I'm calling a final velocity over here, is a lot larger of a number in terms of its magnitude than this initial velocity down here. So it is speeding up while moving in the positive direction. Great. Next question. What does the slope of this line represent physically? Pause the video and make sure you answer that correctly. All right, so the slope is equal to the acceleration of the object. And we can see that expressed here in the formula. If we look over, it's right there. And now what I'd like you to do is solve for A. Isolate it on one side of the equal sign, and then do as much algebra as you can when you do that, and then see what you're looking at. So try that. A is equal to, I'll give you a hint, obviously there's going to be some division. All right, pause the video and work that out. All right, it should be easy for you. You just subtract over the initial velocity here, and then we can turn this into the change in velocity divided by the change in time. Notice I'm not starting today at an initial clock reading of 0 seconds, as I typically do. So I'm using time interval here to be proper, and then we'll talk about how we can make that a little bit simpler towards the end. Okay, so now you understand hopefully what this graph is communicating. We've talked about the slope, and we've looked at our what's called our first equation of motion here, and learned how to calculate our acceleration, all in variables. There's one more thing that you need here in this problem, and I'm going to go ahead and start doing this. So I'm with my laser pointer here, trying to shade in this area, right? And I want you to pause the video and write down on your paper, what did we learn, or what is the area underneath the velocity versus time graph represent? So I'll write that out. What is the area under a velocity versus time graph? This is a big concept. So pause and recall what that is before moving on. Well, the area under a velocity time graph is the displacement of the object during that time interval. Cool. Well, that's just a word right now. Let's turn displacement into a symbol that we've learned. And we know that displacement is delta x, or the change in the position. Change in position. All right. Well, with that, now you're ready to kind of dig in and derive this yourself. However, what I'll tell you next is what I want your final answer to be in terms of. So I'll give you the formulas, or sorry, I'll give you the symbols and the variables that you will see in your final result, and kind of constrain you to only use those things, just so you know kind of if you're on the right track. So we'll write that out now. All right, so your final answer here, when you do this derivation correctly, you'll have final position on the left equals some combination with math of the time interval, the acceleration, the initial velocity, and then the initial position. Now, you notice this is important. The initial velocity is all I'm allowing over here, meaning you will not have the final velocity in your equation, and you won't have the change in velocity in your equation. You can see those variables are up in this section when we were working on that, right? But I'm not allowing you to have either of those variables in your final result, just the initial velocity. So if you work out the math correctly and you get it in the right form, then you'll see that that will work. And a final hint here, take a look, and I'll just draw a line like this. Oops. And then if you look visually at everything on the page in terms of the area and all these equations and symbols, I know there's a lot going on, but this is a good challenge for you at this stage in the game to try to figure out and do a theoretical derivation here in physics. All right, so pause the video and really make sure you don't just skip ahead to the solution. It's really important to put yourself in kind of this moment of struggle to work with all this so you can see what you're having problems with as you push through the math and you work more abstractly with symbols, etc. This is hopefully going to be challenging for you. And if it's easy, well, then that's great too. But spend some serious time trying to get this, and then we'll take a look. All right, pause and have some fun. All right, so let's push forwards here a little bit, and I'm going to kind of slowly work through this and give you some hints. That way, you know, you might see if you got a certain part, and then you can pause the video again and keep going, right? And hopefully you saw that the area here underneath this line, the area underneath this line is a right triangle and a rectangle. So if you got that, excellent. Now you got to convert this into the symbols in physics. What did the area represent again? And then how do we calculate the area of a right triangle and then of a rectangle? Okay, well, let's just write it out. The area represented the displacement, right? So that goes there. And then we'll write out that this is 1/2 the base times the height. These are just generic formulas right now. And then this, of course, is length times width. All right. So I'll pause here. And now you got to convert these non-physics variables of base and height on the graph here into some physics variables. And then same with length and width here. All right. And then work with all the math and do the algebra and see if you can get it. All right. So there's a huge hint. Hopefully you got that. But now keep pushing through and see if you can get to the final result. All right, well, this next step, let's take a look at the triangle. 1/2 by the base times the height. So what is this here? Well, it's not a physical length. Please realize that. This is not a distance. Instead, on the graph, if you were to compute this line, it would be a final clock reading minus an initial clock reading, or a change in time, or a time interval. All right, so delta t is what that is. And then likewise here, this is not a physical distance in space. It's abstractly the final velocity minus the initial velocity, or the change in velocity. Okay, so we can use that. Let's write that in over here. And we see that we would get 1/2. Oops, let me do this in same color. 1/2 the base times the height, so delta t times delta v. Cool. And then for the rectangle, well, we can see that the length is delta t. So that's this distance here. And then what about this, which I'll call the width, I guess. What would that be? Well, that's just the initial velocity. You can see the graph goes from 0 up to the initial velocity there. So we'd multiply that. All right, there we go. All right, now I'll leave it like this. We're not done yet, but we're almost there. Okay. However, notice that what's not in our formula right now that we said that we needed to have by the very end, if you look at it for a second. Well, I don't see anything to do with acceleration, so that's a problem that you'll need to solve. And then the other issue is we've got this change in velocity here. And we said we didn't want that. So we got to figure out how to get rid of those two problems and work through the math. So pause the video and keep going to see if you can get it. All right, so down here on the lower left, I've reminded you of our first equation of motion here. And then remember, we rearranged that to solve for the acceleration. So hopefully you saw to do that. And you needed to solve for the change in velocity here algebraically. So when we do that, we notice, I'll just do that kind of down here, that the change in the velocity of an object is going to equal acceleration of it multiplied by some change in time. So we'll plug that in. We have our displacement equals 1/2 delta t, and then multiplied by a delta t plus delta t, and then vi. Okay. Cool. Now we're almost done. Let's continue with the math, and typically we write it 1/2 a and then delta t times delta t. What would that equal? I find a lot of students actually kind of mess this one up, so I'll actually just write it out like this for a second. Okay, and then over here we'll do the same thing. We'll put the delta t on the other side. That looks pretty good. And just watch out when you do this, delta t times delta t, that's going to give you delta t squared. Doesn't give you 2 delta t. I've seen many students make that mistake. So we'll put that in parentheses and we'll square that. And then we're almost there. Last thing, remember, I wanted an equation that would allow us to predict the final position with all this other stuff, right? We don't have that right now. What's on the left-hand side over here? Let me just get rid of this t here. What's over on the left-hand side is not final position. It is the change in position. So go ahead, pause the video, and see how you can now turn this into something to do with final position. Okay, go ahead. All right, well now you should have thought, well, what is a displacement? It's a change in position. That's a final position minus an initial position. And now we can just bring this term minus the initial position all the way over to the other side. It becomes a plus, the rules of algebra, and we end up getting our final result of the final position equaling 1/2 times the acceleration multiplied by the square of the time interval plus the initial velocity multiplied by our time interval. And we'll write this out neatly on another slide as well, but that's our final result. Oops, no, it's not, right? What did I forget to do? Yeah, hopefully you caught that mistake. Plus the initial velocity times our time interval, and then we have to add over this initial position. Now we're good to go. We'll put a box around that. And there's our final result. All right, now there's a lot going on here. Look at everything on this slide, right? We're doing some heavy lifting with the derivation. But it's important to be able to do this skill in physics to really see where our equations come from. We don't always do derivations, but for like really key things we do, and this is one of those. All right, well here it is. And let's unpack this. Like, what is this really saying? A couple notational things first. We'll drop the time interval or delta t symbol, and we'll just assume that our clock's always going to start at 0 seconds, and then that allows us to make this t final, just turn that into a t. It just cuts down on a lot of the notation with the subscripts and allows you to focus a little bit more clearly on more important subscripting such as initial velocity and initial position there. All right, so we'll do that. And then let's think about what this is saying. And to help you see that, I'm going to cross something out right now. So check this out. Okay, that's gone. Now look at the equation and think to yourself, what are you looking at? Have we seen this equation before? Pause the video. Think about it. The answer is yeah, we've seen this before. This is just the good old constant velocity model, which says if we want to know a final position, tell me my initial position, and then I'm going to add to that some other thing that has to do with how fast I was moving and how much time I moved for right here. As long as this symbol v stands for some constant amount of velocity, then that'll exactly predict my final position. But now we're seeing that when we allow things to speed up and slow down and have acceleration, and we work through all the math, we get a new term popping up. And that term's right here. It's 1/2 at squared. This is incredible. We don't even have to know all the velocities in between. We could start at 0 and go all the way up to 100 miles an hour and have really no idea about what the particular individual velocities are in some big master table that we'd have to like try to plug into some crazy looking formula. We can consolidate all that information into one number here, the acceleration value, and then as long as we know an initial velocity, we can predict where we're located. That's pretty incredible. Now let's go even further. Whenever we do a derivation in physics with some theory work, we always want to check for consistency with units. So I'd like you to do that now. We know over on the left we have to have meters. That's not mass or anything. That's just m for meters. Okay. Um, so determine the units of this term. And what I mean by a term is this whole thing. Let me be specific here. That's a term, this is a term, and this is a term. Okay, so you'll get some units, some units, and some units, and there's only one possible result that you can get. We have to have meters plus meters plus meters. So prove that we get meters, meters, and meters. Pause the video and try it. All right, well, let's take a look. This is such a massive skill in physics because oftentimes you'll be working on a problem and you won't know if you exactly got the right answer, but you can check your units to make sure it all matches up, and then there's a good chance that you probably are doing something right. So if we look here, acceleration has units of meters per second squared. Of course, the number 1/2 is unitless. That's just a constant. And then look, we're squaring time. So we have to square seconds and we get seconds squared. This cancels right there. So we're left with meters in the first term. Next, we've seen this before. Seconds cancel out on the bottom and the top there, and we're left with meters, and then obviously initial position is in units of meters. So we've checked it. Everything looks great and consistent. All right, now there's a million ways to apply this equation of motion and solve for things and start to get used to kind of how it behaves. And we'll do that in other videos and problems that we'll see. What I want to do to conclude the video is we'll write out our first equation of motion, now what I like to call our second equation of motion, and then I'll show you how you can find even a third one, and I'll give you a hint on how to find it if you want to go do that, and then right at the end I'll give you that third equation of motion. So let's consolidate everything together into what I tend to like to call the three equations of motion. All right, so here they are. We'll get to the third in a second. The first one we've seen before. It just allows you to predict your final velocity if you know some initial velocity and some acceleration value in the clock reading, or the amount of time you allow to elapse on the clock. The second one we just derived allows us to know exactly where something's located after a certain amount of time has elapsed when we are accelerating at some rate. And then we also need to know our initial velocity when the clock read 0, and then our initial position as well. Notice that we don't have to know any velocity in between or a final velocity or anything like that. It's the initial velocity here that counts in this term. Now, what you should notice about both of these equations, even though they are different, they both include one similar variable, and that is they both have time in them. So you have to know something about time in order to determine these parameters. So there's a way to get rid of time if you do a lot of algebra and combine these two equations. And I suggest you try that if you'd like to. It's a good amount of like algebraic manipulation. You don't have to if you don't want to, but it's a nice exercise. And you can work it all the way down into an equation that does not have any time in it at all. And I'll write down right now what it will have in it. And the right way to write it is you'd have final velocity squared over on this side, that's typically how it's written, is equal to, and then the stuff that you're only allowed to have over here is going to end up being acceleration, your initial velocity, and there's a couple ways to write this. We'll do it, we'll end up doing it both ways, but we'll do it like this for now with the displacement there. Okay, so pause the video if you want to try that and see if you can derive this third equation of motion without time, and then I'll give it to you right now. All right, well here it is. It says that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by, careful, this is displacement. So it's final position minus initial position in some parentheses, quantity, right? So just watch out. People can often forget that this is displacement here. And there we have it. These are the three equations of motion. Some people like to do 5 equations, other people have 4. But those are just kind of, they tend to be, manipulations of these to other forms for ease of use. I tend to like to just use these 3. It kind of gets to the core ideas of working in one-dimensional kinematics and describing motion in the most simple way. Okay, so we'll learn how to use these in great detail. And one kind of final point, I guess, that I'll share with you is in the back of your mind, as we solve these problems, I want you to, remember to not look at these equations just as kind of things that we'll end up plugging numbers into to get answers, but really more as guides for our thinking. There's a lot of things that are being said here in these math statements, and it's not just about plugging and chugging. There's some very deep concepts kind of embedded in these three equations, and so much you can unlock about how the world works now with these three equations that we're going to see in many different contexts. So just remember that as we go through. They're not just equations, they're kind of telling a story of how things move in one dimension. And we want to kind of unfold that story over time by looking at great problems. And that's what we'll do. Okay, so hope you enjoyed that. Nice derivation here of our three equations of motion. And take care. We'll see you next time.